you haven't given me your homework yet, then please do so at the end of the lecture. And do so quickly because I have to rush and do something else after the lecture. Okay, so now I want to go back to our technical effort. We want to be able to describe the evolution of underlying asset prices and then to use that to find prices of derivatives. And we got to this point, but let me remind you how we got to this point. We started by saying we need a good model of the evolution of share prices. So we're going to look at Brownian motion. And that's going to give us some inspiration for that. What was Brownian motion? It was a stochastic process, which is a family of random variables indexed by time. And then we said, well, that's very nice, but we need something. I'd like to start the lecture, please. We said Brownian motion is very nice, but that's not enough. We need to have something which has Brownian motion in it to describe the jiggling up and down of prices. And then what did we decide to do? We said we want to look at the change in the underlying asset price value. And I want to model this by saying that an infinitesimal change in the price is going to have two components. Sorry, is there a question there at the back? Okay, so in that case, let me start my lecture. So we said the change in price is going to have two components. One of them is going to be proportional to the period of time over which the change is observed, and the other one is going to be proportional to the change in the position of a particle following Brownian motion. And we said which model precisely are we going to use? Then we said we want the proportional change in the underlying asset price to be some constant, which we're calling mu, times dt plus another constant which we're calling sigma times d Brownian motion, and then we can multiply both sides by s, and that's how we formulate our model for the evolution of underlying asset prices. And then to do this, we needed to find a way to construct these s's which satisfy this condition. And that's the point where we introduce Ito integration. We said, okay, if we just had this bit over here, I know how to find an S that satisfies this. This is regular integration, which we all know and love. But how do we deal with this? And then I told you how to integrate such a term, how to integrate with respect to Brownian motion. So that was the Ito integral. Once we've done that, I tell you I want an S that satisfies this condition on the infinitesimal change in S, and then I have the tools to construct it. So there is such an S, and that's the S that we're going to use to model the underlying asset prices. And then I said, well, that's not enough. I want to take functions of processes like these. So a process X, an Ito process, has the form. So it's a stochastic process, and I specify the stochastic process by saying what is the infinitesimal change in the value of x. And in general, it's going to have two contributions to the change, one of them proportional to the period of time, the other one proportional to the change in the position of a particle following Brownian motion. And we write it as A dt plus B dB. So we start with an Ito process x, and we're going to have to look at a function of this x and time. So as in the slide here, we have a process x, which is an Ito process, and it's given by that. dx is that expression up there. And we have a function d of two variables, little x and t, which is nice in the sense that it's twice continuously differentiable with respect to x and differentiable with respect to continuously differentiable with respect to time. And we look at the new process y, which is the function g of x in time. Now, for every time t, I can look at this random variable and I get this random variable. So what I'm defining is a family of random variables indexed by time, which is what we are calling a stochastic process. And then if I give you a stochastic process, you can ask what sort of stochastic process this is. And Ito's lemma, which is what we're trying to do, what we're trying to convince ourselves makes sense, says that this new stochastic process is an Ito process. It has the same form as x, so it's going to be something times dt plus something times d Brownian motion. And the question is, once you know that it has that form, what are the somethings? And Ito's lemma says, here it is. dy is this expression over here times dt plus this expression over here db. Now, this looks very complicated. Let me convince you that it's mostly not too complicated. There's only one weird thing there. So suppose that, and this is not true. So from now on until I say otherwise, so the following is nonsense. So if you do copy this down, please copy down this proviso too. So if B was not this complicated stochastic process, Brownian motion, suppose it was a variable. If B were a variable. Okay, and now I have a function x of time and the variable b, and then I have a function g of x and time, and I ask myself, and y is g of x in time, and I ask myself, how does y change? Why does y change? Y would change under this assumption because the variable t change and the variable b change. So let's see. What's the contribution to the change of y? Well, there's going to be a change in time. Sorry, let's do it like this. There's going to be a change that comes from the fact that this is changing. So let's measure that. So there's going to be the sensitivity of g with respect to the first variable, the partial derivative of g with respect to x. And now there's going to be the change in x with respect to time. So if x is that form over here, we're going to have an ADT. And there's also going to be a change in x, which comes from the second term over there, BDB. Okay, so that's one reason why y, which is a function g of x and t, is changing. The other reason is because the second variable is changing. So how does that happen? Well, I look at the sensitivity with respect to the second variable, and then here I have to multiply by dt. This is why the function g of x and t is changing. It's changing because this is changing and because of this is changing, and then you take the sensitivity of g with respect to the change here times the change in this, dx is that, and then you take the sensitivity of g with respect to t, and t is just a variable. Okay, so if we compare this with that, what do we see? We have dg dx times a times dt. That explains this term over here. We have this term over here, which is the term dg dt times, sorry, the derivative of g with respect to t times dt. So we explain this term over here. There's also this term over here, dg dx bdb, which is this term over here. So if b was just a variable and not this complicated stochastic process, we would be getting that without this term here. So what I have to do is I have to explain to you where this term is coming from. Okay? And how am I going to explain that? The crucial ingredient, which I'm waving my hands to justify, I'm not giving you a proof, is what we've seen last time. So if you take the dB squared, you're getting dt. If you take the square of the change in the position of a particle following Brownian motion, what you're getting is the length of time over which this Brownian motion happened. Okay? Okay, and last time I tried to convince you this is true, and that's the argument if you want to refresh your memory. And now let's put everything together and let's see if I can convince you that Ito's lemma is making sense. So how do I compute this? How do I compute the change in the value of a function? So one standard technique is to look at the Taylor expansion of your function g around your point. So around the point xt. So how do we find the change in the function that comes from observing the Taylor series? Well, you look at the derivative with respect to the first variable times the change in the first variable, plus the derivative in the second variable times the change in the second variable. And then you start taking terms of order 2. So it's going to be the second derivative with respect to the first variable times the square of the change in the second variable, and so on. And then you finish with the quadratic terms, and then they're going to have terms of degree 3 and 4 and so on. We're going to be looking at this when delta x and delta t are very small, so we can safely ignore the negligible contribution of higher order terms. And now I go here and I look at this term over here. Delta x, according to a model, according to the fact that x is this Ito process over there, is given by this, and then I'm looking at the square of that. When I take the square of that, I'm going to get terms which are quadratic. So for example, I'm going to have a squared delta t squared. If delta t is minute, then delta t squared is going to be completely negligible. And then I'm going to have a delta t delta b a dB term, which again, since both of them are going to be tiny, the product is going to be negligible. But then we end up also looking at b squared dB squared. dB squared, which looks like a quadratic term, is in fact, because of the previous slide, is a linear term. It's dB squared seems to be the same as delta t. So instead of that, instead of b dB squared, we're going to write b squared delta t. We get this linear term. And here again, if you expand and you check what this is, everything in here is going to have terms of degree 2 in delta t and delta b, and the same thing here. So we can ignore all the other terms. So we're going to take this Taylor expansion, and when we look at all the terms beyond this one over here, we're going to ignore them, they're negligible. And then when we look at this one over here, it has a contribution of b squared delta t. Okay, so we can put everything together and we ask ourselves, for very small delta t, what is the change in y? Then we said we get this plus terms of higher degree in delta x and delta t, which we're going to ignore. So if this is what we're getting, now we can expand back what delta x is. Delta x, according to our assumption, is a delta t plus b delta b. And we're getting this. And now take delta t smaller and smaller, replace delta t with an infinitesimal dt and delta b with an infinitesimal db. And what you're getting is that dy is what Ito's lemma is telling you it is. Just put together all the terms with dt, and you're going to get Ito's lemma. Okay. So again, this is not quite a proof, but it's a good argument to show you that Ito's lemma makes sense. So this is what happens when b is a variable, and that is what happens when B is this strange thing, so that dB squared is dt. Okay? Do you have any questions about Ito's lemma? You should have questions. You should be asking me all, why on earth are you showing us Ito's lemma? Why are we suffering? So I'm going to show you the suffering, and I'm going to show you the end of the suffering and its fruits. And that's going to happen at the end of this lecture, I think. Okay, now before we start collecting the fruits of Ito's lemma, let's see some examples. Let's make sure that we know what it says and how to use it. So let's use Ito's lemma to show that. So what am I doing here? I'm saying Bt is a Brownian motion, the stochastic process that we all know and love. Okay? I don't want to look at this stochastic process. I want to look at a new stochastic process. What is the new stochastic process? Is you take each one of these random variables and you square them. It's a new stochastic process. And now I ask you, what sort of stochastic process is that? Then what are you going to say? You're going to say, how do I get this from that? So I have a function g of x and t, which is given by x squared. And this is nothing but g of bt. Right? Aha, so we seem to be in the setting in which Ito's lemma can help us. We have a stochastic process, which is an Ito process. Brownian motion is an Ito process. Why is Brownian motion an Ito process? Can I write d Brownian motion as something times dt plus something times d Brownian motion? You can. You can even tell me how to, you're just not telling me. How do we do that? How do we make this true? We put here what? Starts with a z. 0, and we put a 1 here. Yeah? So that's how you convince yourself that Brownian motion is an Ito process. D Brownian motion has that form. So we have a function of an Ito process in time. Ito's lemma says it's a new Ito process, and I can tell you exactly, if you call this y, I can tell you exactly what Ito process. I just need to compute that. So let's compute that. What is dy? What is d Brownian motion squared? So what do I have to do? I have to take my function and take the derivative with respect to the first variable. So let's do that. dg dx is 2x. And we're going to need the second derivative, which gives us 2. And we also need the derivative of g with respect to time, which is 0. And now we go to Ito's lemma, which I conveniently repeated there, and we start plugging things. So let's see, we have dg dx, which is this. So we're going to take 2 Brownian motions, and we're going to have to multiply by a. What is a? This is what in Ito's lemma we're calling a, and this is what in Ito's lemma we're calling b. So we're going to multiply this by 0. Yeah? And then we have plus dg dt, which is 0. And then we're going to have plus what? The second derivative of g with respect to x, applied at Brownian motion in time. So 2, and I plug in Brownian motion in time in 2, so I get 2. And then I have to multiply by 1/2 and by b squared. 2 times 1/2 is 1, times b squared is 1. And I'm getting this coefficient of dt plus something times d Brownian motion. So what is the something multiplying d Brownian motion? I go to Ito's lemma and it says, take dg dx, here it is, 2 times Brownian motion, and I multiply this by b, which is 1, and I get 2 Brownian motion times dB. Okay? Do you see where this is coming from? Is this making sense? Okay, if this is making sense, then let's use this to say something useful. Let's use this to deduce that the Ito integral, look, this is one of these things that we worked hard to produce. We took the period of time between 0 and t, we sliced it into slices. Yes?
You missed out an x on the 2b, because isn't it the first two?
Okay, so the question is, what is this? Is this true? So what should I write here? So I should write dg dx evaluated at whatever I'm plugging in into my function g. What am I plugging in into my function g? I'm plugging in the Brownian motion and time. So I have to evaluate this at x equals b. So that gives me a 2b. And then I get a 0 coming from here. Ask me questions. This is really confusing stuff. You should all be really confused, and you should all be really asking me lots of questions. And any other questions about this calculation? Okay. So now let's put this equality we just showed to work, and let's use it to show something else. And here's the thing that I want to show. I want to look at this Ito integral, this thing that we define by slicing the time period between 0 and t and writing down its sum and then taking limits when the slices are thinner and thinner. Let's use this to show that this complicated object, this complicated random variable, is given by this. So how do we do that? So let's look at the square of that's not what I want. Let's look at the square of Brownian motion. And let's have a look at d of the square of Brownian motion. Suppose that I come to you and I say, I want to know what is the integral. Sorry, suppose that I want to know. Okay, let me first finish writing this, and then I'll tell you what I want to know. So we just showed that this dB squared is dt plus 2b dB. Suppose you come to me and you say, I want to know what is the process whose differential is that. Yeah? I can do this in two different ways. One way is for me to move my hand and to read what's written here, right? That's the process whose differential is that. Another way of doing this is to say, okay, you integrate this. This is how we found processes given by the differentials. If the differential was given by something of this form, how do you find the process? You integrate this. You integrate this with respect to dt, and you Ito integrate this with respect to d Brownian motion. So on the other hand, we know that this is b of 0 plus the integral between 0 and t. I don't want to integrate with respect to t because I have a t here, so let's call this ds, plus the Ito integral from 0 to t of 2b d Brownian motion. So let's write it like that. Okay? Now, b of 0, Brownian motion at 0, by property 1 of Brownian motion, this is just 0, so we can ignore that. And what are we getting here? We're getting that. Brownian motion, if you look at Brownian motion time t, it's given by that. Okay, that's great, because now I can also look at this integral over here. This is just t. And if I want to know what is this integral, well, I can pull a 2 outside. I can bring this to the other side and then divide everything by 2, and what I'm getting is this expression over here. So I'm just solving for this, right? Do you understand the second part of this example? So here's an example in which Ito's lemma is useful when you're trying to find Ito's integrals. Okay, so here are the details again. So we look at the stochastic process B, which is an Ito process because you can write for this particular x equals b, you can write dx as 0 dt plus 1 db. And then you look at y, which is a function of x and t given by the square of x. And then you compute these derivatives. You use Ito's lemma to try to find what is dy, or d square of Brownian motion. You use Ito's lemma, you get this. And then you integrate both sides, and you get that. And then you solve for the Ito integral we're trying to find, and you get this. Right? Okay. Let's see another example. And I'm going to show you 2 examples. The second one is going to be very important. But let's start with the first one. So let's have a look at forward prices. So suppose that I'm looking at forward prices in the future. So remember, if I enter a forward contract now to deliver something, say at time capital T, I can compute what is the forward price. What is the forward price for something delivered in T years? So let's call this f of 0, or f of 0. What is that? Well, it's S of 0, which is the spot price of this asset to be delivered in T years, times e to the interest rate, T-year interest rate, times T. So this is what we've done at the very beginning of this course. We found forward prices. Okay? Now, I can ask myself, let's look at some point in the future, some point T in time between 0 and delivery. Then there's going to be some forward price observed at that time. I don't know what it is. If I don't know what it is, then when I talk about the forward time at this time t, I'm talking about the random variable. What do I know about this random variable? Whatever it is, it must satisfy that this is e to the interest rate, which I assume is the same always, times time to delivery. What is time to delivery? Is delivery time minus time t times the underlying asset price at time t. Right? This relationship always holds. That's what we know about forward prices. So now let's ask ourselves, okay, so I don't know what this is. These are random variables. We have a family of random variables, f of t indexed by time t. What sort of random variables are these? Okay? So we look at this and we say, this family of random variables, that if you prefer, you can think of as being S, f of t, and I'm looking at the collection of all these random variables, f of t, when t is greater or equal to 0. This random variable, this stochastic process is defined as a function of this other stochastic process and time. Okay? And this is not just a stochastic process. We have a model that describes S. What is our model for S? Here it is. So how can we find what sort of stochastic process is f? F is a function of time and an Ito process. F is going to be an Ito process itself. So what do I know? I know that the infinitesimal change of f is going to be something times dt plus something times dB. Which something and which something, Ito's lemma is going to tell us. And we have it up there. So let's see. What is f? F is a function g of s and t. Which function of s and t? It's going to be s times e to the r t minus t. Okay, so let's see. What do I have to do? To find out what to write here, I have to take the function g, take the derivative with respect to the first variable, and plug in s and t. So we're going to have to know what is g. Let's think of g as a function of little s and t. Let's find what is g dg ds. So what is dg ds? It's e to the r t minus t. Let's find the second derivative of g with respect to s. That's going to be the derivative of this with respect to s, which is 0. And we're also going to need the derivative of g with respect to t. So let's see, we're going to have an s, which doesn't play much of a role, and then we have to take the derivative of this with respect to t. So we're going to get this times minus r. Minus this times r times e to the t minus t. Okay. So these are the partial derivatives that we're going to need to apply Ito's lemma. And now let's remember that we have this model for S. And now let's use Ito's lemma. So what does Ito's lemma say? It says take the derivative of your function g with respect to the first variable. Here it is. And multiply this by a. What is a in our case? A is mu s. This is what we call in Ito's lemma A, and this is what we call in Ito's lemma B. Okay, so the first term is going to be this evaluated at S and capital S and T times A. So we're going to have mu S times this. That's the first term you see there. And then we're going to have plus 1/2 this evaluated at S and T times b squared. Now this is 0, so it doesn't give us any contribution. And then we're going to have to add the derivative of g with respect to t. The derivative of g with respect to t is this. So we write this there. So that's the coefficient of dt. That's what Ito's lemma tells us to write here. And then we're going to have a coefficient of db. We go to Ito's lemma and we say, what do we have to put there? We have to take the derivative of g with respect to the first variable, there it is, times b. And b is sigma s, according to our model, there it is. So we write this times sigma s db. So this is what goes inside here. Okay? And now we look at this and we go back to what we know about f. So whenever we see an e to the r t minus ts, we substitute this with an f, and this is what we're getting. Is this calculation making sense? Okay, so now that we are confident with using Ito's lemma, let's apply it to a situation which is going to be important for us later. And here it is. Let's have a look at the logarithm of asset prices. Very nice things are going to happen here. So we start with the Ito process S, described by that. And I'm going to take a function g of little s and t, and it's going to be the natural logarithm of s. Okay? And then I'm going to define a new stochastic process, which I'm going to call, let's call it y, which is going to be g of s and t. What is this? Two words. Starts with S and P, or two words starts with I and P. For any t, this is a random variable. This is a function of random variable in time, so it's a random variable. So each one of these is a random variable. We have a collection of random variables indexed by time. It's a stochastic process. Ito's lemma says this is not just a stochastic process, it's a Ito process. So So we know that dy is going to be something times dt plus something times dB. And we have to figure out what goes in there. How do we figure out what goes in there? We use Ito's lemma. There is Ito's lemma. So what is Ito's lemma going to tell us? It's going to tell us, well, compute a few derivatives. So let's take g, the derivative of g with respect to the first variable. We get 1 over s. With the second derivative with respect to the first variable, we get minus 1 over s squared. We look at the derivative of g with respect to time. There's no time here. We get 0, and now we say, okay, what does d log s is? What is dg of s and t is? Well, we go to Ito's lemma. We say, take dg, the derivative of g with respect to the first variable, which is 1 over s, and plug in capital S and time, and then we're going to get 1 over s. Multiply that by a. What is a? Is mu s. So that's the first thing we get from Ito's lemma. Then Ito's lemma is telling us take dg dt, which is 0. So we don't have a contribution from that. And then it says take 1/2 times the second derivative of g with respect to the first variable, which is minus 1 over s squared. So it says take plus 1/2 times minus 1 over s squared times b squared. What is b squared? B is this. So it's s squared sigma squared. So we put everything together and we're getting this. And this expression I just wrote here is a coefficient of dt for d log s. And then we also have to find the coefficient of dB. How do we do that? We go to Ito's lemma. We say take the derivative of g with respect to the first variable, which is 1 over s, plug in capital S and t. So we're getting 1 over s, and multiply by b, which is sigma s. And we're getting that. Okay? That's Ito's lemma. And now lots of s's cancel each other, and we get this. And this is amazingly good. Why is this amazingly good? We know exactly what the logarithm of s is. How do I know exactly what the logarithm of s is? D log s is this beautiful thing. Mu minus sigma squared over 2 dt plus sigma dB. This is about as simple as life can get. Why is that? Suppose I ask you, great, so tell me, what is log s? Let's be completely precise. What is log s at time t? What do you say? You say, well, we know what this is. You taught us it's log of s at time 0 plus the integral of this. The integral of this between 0 and t. Fine. What is the integral of this between 0 and t? Mu minus sigma squared. This is just a number, right? And how about this? Plus, let's write it like this, integral between 0 and t of sigma dB. What sort of integral is this? It's one of these difficult Ito integrals, but not very difficult because I move this sigma outside. What's the integral of d Brownian motion? It's Brownian motion, right? Because as before, if I ask you, how do you find what is the integral of d Brownian motion? Well, how am I going to say that? Let me retrace my steps. Let me show you a better way of thinking about this. How do I find this integral? I chop this time interval from 0 to t into small slices. For each slice, I compute 1 times the difference in Brownian motion. I add all these slices together. So what do I get? I'm adding all the differences in Brownian motion. what do I get when I sum all the differences bt1 minus bt0 plus bt2 minus bt1 and so on up to btn minus btn minus 1. What do I do when I sum all this together? Well, this is going to cancel that, and this is going to cancel here, and this is going to be cancelled by this one over here, and at the end of this big process, I'm just getting btn minus bt0, in our case, b of t minus b of 0, which is just another way of saying b of t. b of 0 is 0. Okay, so we look at this and we say, we know what, where am I? We know what the logarithm of s of t is. We get this, plus this normal integral that we know how to compute, plus this, which we can now write as sigma times b. And now we say, okay, but we know what this is. What is this? This random variable. Let's write it as bt minus b0. What does the second property of Brownian motion tell us about this random variable? This difference is normally distributed with min 0 and variance t. So this is normally distributed min 0 and variance t. This is property 2 of Brownian motion. So now we look at this and we say, we know all there is to know about this random variable. It's this number plus this random variable, which we understand completely. We have sigma times this normally distributed random variable with min 0 and variance t. Sigma times that is normally distributed with the same mean of 0 and with variance sigma squared. So now let me repeat myself a bit. So if you look at log of st minus log of s0, so if I bring this to the other side, you're getting a random variable which is this number over here plus this random variable with min 0. So we get a random variable which is normally distributed with this min. There is the min. And the variance is sigma squared times t. So this at variance t, and this is variance sigma t squared. To make this accord to what's written in the slides, I'm using capital T for notation here. So replace all the little t's with capital T, and you're going to get that expression over there. Is this making sense? Do you understand this example? Okay, so now there's another little thing here which I'm going to skip, another example which I'm not going to do. And now I want to show you the promised land. This is where we were marching all this time. And I'm going to give you a first glimpse of it, and we're going to get there in full detail next lecture. So I'm going to fulfill my promise, and I'm going to write down a formula for the prices of European options. So let's start by making an assumption. Suppose that I look at some derivative, some asset whose price depends on the price of some other asset. And suppose that other asset is a price S which behaves like this, which follows our model for the evolution of asset prices. Then the assumption we're going to make is that the value of this derivative, the price of this derivative, is going to be a function of the underlying asset price. Okay? So you ask yourself, I have this derivative, whose underlying asset price behaves like that, and that derivative at time t is a price which I'm going to call f, and I want to know what is f at time t in the future. then the answer is going to be that f, the price of your derivative, is going to be so f at time t is going to be a function of the underlying asset price at time t and time. Okay, makes sense. If you have a call option on IBM shares, then the price of the call options on IBM shares should depend on the price of IBM shares. It should also depend on, say, the time to the expiration of the option. So this assumption sort of makes sense. And then, if this is the case, how do we find f? So that's what we're going to do next. So the aim of this section is to find the prices of European options, and we are going to make the assumption that the prices of options are functions of the underlying asset price in time. We're going to assume that the underlying asset evolves according to this model. That's our standard model for the evolution of underlying asset prices. And now we are going to give a name to the price at some time t of some derivative contingent on the value of the underlying asset price, what we're calling S, and we want to find the price of this derivative at time t. So the price of this derivative at time t is a function of t, of course, and the price of the underlying asset at time t. So to be completely specific, we should write here S of t. Okay, now we don't know what this function f is. This is what we're trying to find. We're trying to find an expression for the price. But now, let me show you what's going to be our first step. Let's make the assumption that this function f is a nice function. It's twice differentiable with respect to the first variable and differentiable with respect to the second variable. Continuously twice differentiable and differentiable. Then we can take this function and we look at it and we say, we know what this is. This is a function of an eta process in time. This is going to be a new eta process. And we know which new eta process it's going to be. We use Ito's lemma. So here's what Ito's lemma is going to tell us. This is what we get from Ito's lemma, which is written up there, when instead of G we have a little f, and when A is mu S and B is